Hi everyone and welcome to my channel. Today I want to talk a little bit about recursion, a little bit about what it is, a few examples, and when you might want to use an iterative approach versus recursion. So firstly, what it is, it's basically when a function calls itself. It's a simple concept to understand but often takes time for developers to begin to think recursively. But once they do begin to think recursively, it's often the most logical solution when involving data structures such as trees, and there are a few other cases where it makes sense to do it as well. I've kind of come up with my own way of thinking about recursion so that I don't get it wrong, and I've called this just the recursion checklist. So basically you're going to want to have a base case. This is basically something that you're working towards each time you're calling the recursive function. And basically it's to ensure that it doesn't infinitely keep calling itself. The base case is where the recursive function stops calling itself. It's basically very similar to a loop condition, and I'll show you a few examples and show you what the base case would be. Then you're also going to need the recursive call, obviously, otherwise it's not going to be a recursive function, and it's just going to move towards the base case, and it's basically you're just calling a method from within itself. So one of the biggest examples of recursion is the Fibonacci sequence. So basically with the Fibonacci algorithm, you're going to want to find the nth element of the Fibonacci sequence. This is the sum of the two elements prior to it in the sequence, and it lends itself nicely to recursion, but you can also solve by an iterative approach. When you're solving by recursion, it's terribly inefficient with exponential time complexity. So let me show you the recursive Fibonacci function. So you can basically see when n is equal to 0 or 1, you'll return n. And if it is not equal to 0 or 1, then you'll return Fibonacci, which is the recursive function, n minus 1 plus Fibonacci n minus 2, because you're summing the two previous Fibonacci elements. So why that's terribly inefficient is basically it'll go off and call that, and then for each of these it'll then call so it'll go, say it goes to n minus 2, then it will call n minus 2 minus 1 and n minus 2 minus 2 if you were to substitute the value of what you've called here. So and then this one will do the exact same, so you're actually calculating the same values multiple times here because you're doing it recursively and because there's two recursive calls. And this is the base case here that ends recursion because it's no longer calling itself recursively, and we know that that's going to be hit at some point for whenever n is a positive value, because you know that these are always reducing towards 0 and 1. So you can also do it iteratively, and that's by having a counter for the current and a counter for the next, and then looping through I is less than n, so less than the element you want to get, and then just doing a calculation of a temporary value, which is the current plus the next, then setting current equal to next equal to temp, and then just continuously increasing it. This way you're only calculating each element once, so you're sort of progressively going through and adding up until you get to n, rather than working your way backwards from n recursively. And so that's how you get the Fibonacci sequence, the nth element of the Fibonacci sequence iteratively, and it is significantly more efficient. Another example I can give you is getting the root of a tree recursively. So basically we've got this base case here that will end recursion. So if there's no parent, then we'll return this because we're at the root because there's no parent. And if there is a parent, so basically if this condition isn't met, then we'll call parent.getRoot. So we're calling that same function, but we're just calling against a different node, because we've got this reference, a tree-like reference, and it works really well with recursion. You can do that iteratively as well. So you can do while current node.getParent is not equal to null, current node equals current node.getParent, and then when it is equal to null, this will not evaluate to true anymore, and you'll get the value of the root, because because you won't be able to execute this, and so it'll stop executing, and whatever was the value of the current node at that point is the root. So that's how you can do it iteratively. But I find the recursive way for trees, I find it just works quite well. So there's a few things you might want to consider when deciding whether to use recursion. And that's a big one, is how much data are you working with, and is there a simple iterative solution? So when you're considering how much data you're working with, this is a pretty important factor, as if you have too much data and thus very deep recursion, a stack overflow may occur and your program will throw an exception. This is basically when your program tries to use more space than is available on the call stack. The size of the call stack varies depending on a variety of factors, such as machine architecture and programming language. Some languages, such as Scheme, are optimized for infinite tail recursion, and tail recursion is a type of recursion where the return result comes entirely from the recursive call. Most languages are not optimized for infinite tail recursion. So I've just given an example of tail recursion here. So basically you can see this tail recursive function here. It's basically summing down to 0, and I provide a start value to start at and a running total. And when it hits 0, we return the total, and if it's not hit 0, then you'll recursively call sum start minus 1 total plus start. So this is the running total here, and you're saying, okay, I want to sum the previous value, because you're starting at a higher number and working your way down. And because this is a pure return value here, that's tail recursion. But you've also got like all the other types of recursion, and that's like, for example, this, where you're actually calling this function recursively, but you're multiplying it by n, and so that's not tail recursion. So yeah, Scheme, the programming language, optimizes for infinite tail recursion, but not other types of recursion. Another thing I always like to consider is there a simple iterative solution? Because often once you get used to recursion, it's a very natural way to solve quite a lot of problems. However, you should consider whether there's a simple iterative approach that could be used. Generally, these are more efficient as there are less overheads involved, and you are less likely to encounter the risk of stack overflows, so that's another advantage. I hope you've enjoyed this video today, and if you have, please like and subscribe for more content.